So long story is, moreover, if you carefully look at the mathematical structure of the Planck force, you realize this is the superforce. It does not contain h bar, namely the modified reduced Planck constant. Therefore, it can relate to quantum phenomena exhibiting macroscopic classical behavior, namely macroscopic quantum phenomena. Okay, it's a very interesting conjecture. I don't know if it's true or not, but here's the big thing. The whole aka superforce or Planck force is equivalent to the Planck mass times c squared divided by the Planck length. So what's that give us? So if we get a mass, c squared, oh, that gives us an energy, because E equals mc squared. Duh, okay. So, and then when you divide it by the Planck length, you're taking out one Planck unit of length from the Planck energy, which then you'll have mass times the distance, and then that's divided by acceleration, or time squared. So that's going to give us, the Planck force. But what Dr. Pais is pointing out, and I believe others have pointed this out, I think Dirac kind of had the large number hypothesis, but it was framed in a slightly different manner. He was normally comparing, what was it, I think like the radius of the proton to the radius of the observable universe, and it was an interesting thing. So that happens to be of the observable universe. So coincidentally, the whole, if you take mass of universe, so you got a mass times c squared, that should give us the mass energy of universe, and you divide it by the observed radius of the observable universe. And it coincidentally comes out to be right about the same. Okay. So the link is in the doobly-doo if you want to go check that out. So what are we actually talking about? Hey, Sky of Mine, welcome. Thank you for joining. We're going to get into some interesting stuff. And again, is this stuff true? I could be completely wrong. Of course, because that's science. Most things are wrong. But at least math helps give us a little bit of a guidance, so maybe we find an interesting thing. Maybe there's something to it. Maybe there isn't. I think y'all are going to like this, though. Okay. So let's pop up another window. We'll go to our friend Wolfram Alpha, and let's share this. Okay. So we'll just literally do what he had there. Okay, so we do Planck mass, c squared. This will give us the Planck energy. Yep. We get the Planck energy right here. Cool. And then he had it divided by the Planck length, so divide by the Planck length. So, let's go back real quick. So if you're here, energy, its dimensions of energy are a mass times a length, and then it's divided by, mass times length squared divided by a time squared, because, well, length divided by time is a speed. So the maximal speed is c, the speed of light. C squared times a maximal unit mass will give us the maximum unit energy. Cool. Okay. So, and then we would divide that by the Planck length. You're going to get out something in newtons, and that gives us the Planck force. All right, cool. So now let's see what Dr. Pais was talking about. So we'll open another window. So let's take the it's so much easier. You just type it in rather than having to do all the numbers. So the observable universe. So we want the total mass. Okay. So let's get the total mass of universe. Okay, so it's about 10 to the 54 kilograms. Now note, this is the total mass, because if you just do mass, it's just going to do mass of ordinary matter here. Okay, so it's a little bit less, but for the sake of argument, we'll just do the total. Okay, so we'll multiply by c squared. So it'll give us total mass energy of observable universe, according to our best measurements and oh my God, it's multiplying by the charm quark. That's not what we want. We want the speed of light. Okay. It's because we used a bunch of words, so I wasn't quite sure. All right, and we want multiplication. Okay, it's going to give us energy. So this is the total estimated mass energy of our observable universe. Groovy. Okay. So, and then we need to divide it by a length. In this case, the radius of observable universe. Cool. So multiplication and division. Okay. So if we do that, again, 10 to the 44 newtons. Oh, that was the same magnitude as the Planck force. So now it is a little bit off, so let's just see about where we are. So we divide by the Planck force. So it's, what's the multiplication? There we go. Okay. All right. So it's of the order of magnitude. It's off by a little bit because the Planck force begins with a 1. That happened to begin with a 6. But of magnitude, it seems to work pretty well. Okay. Why? So let's go to the board. All right. So as we've been hitting home, the big thing is if we're utilizing SI, aka the metric system, we have a coherent set of units, and those coherent units are set up by this right here. That whole F equals ma, which is force, equals mass times acceleration. E equals F times d, which is energy, equals force times distance. Oh, you kind of see where we're going here. And then over there, it's P, which is power, is equal to energy divided by time. Okay. And then once you have those three rules, and you can go back and forth, back and forth, back and forth, you now have a coherent system, so you don't necessarily need to have different constant factors. Okay. So that's how we get coherence. And then we have different dimensions that we can measure and everything, and we give them different units, unit names. So we get dimensions of length, we get a dimension of mass, we get dimensions of time, we get dimensions of charge, and dimensions of temperature. Now charge and temperature, those are energies, okay? Because if you got some electric charge, hey, maybe you could do some work and stuff. I mean, that's how I'm talking to y'all right now. You gotta use some charge, and computers tend to use power because it requires energy for a period of time, right? Right. There we go. Okay, so we'll get into that. Let's see. All right, welcome, Morgan. Good to see you. Oh, those are some interesting things. I haven't necessarily heard those before. That's very interesting. All right. So, well, here's the thing. Newton did a pretty dang good job in why the heck does the Newtonian gravitational constant have a precision of about 10 to the 7? Or at least 10 to the 7 accuracy, or about 7 decimal places, and then Einstein came along, and he gave us 7 more. That's interesting, but that's not for the sake of the discussion today. The sake of discussion today is, let me erase this so we'll get a little bit more information. All right. So, we're all settling in. Let's, I don't know, we'll keep this here just because I think this is useful. Just to keep it in the corner of our minds. Just because you never know when maybe something will pop up. Okay. So we'll do this. So another fantabulous Monday. I know there's crazy stuff and things going on around the world. We're gearing up for the Domesticon 2025 and apparently the beautiful Sembra, Portugal, hosted by Anastasia and Shiloh from the Demystify Side podcast. Shout out to them. And we actually ordered a bunch of new t-shirts and stuff, so if someone happens to be there, who knows, maybe we'll be able to grab a Physics Monastery t-shirt. We started a few new designs and stuff, and should probably actually link to the store, but that's okay. Okay. So we'll keep this stuff here just for reference because we're gonna work off something. So I forget who it was, but it was some lecture. And do I have this? I think, let me see. It was somebody that had said, a famous physicist, I don't know if it was The Rock or somebody, they had said something along the lines of, our universe must have the same amount of equivalent mass as charge as action. And I'm like, wait. So what you're saying is that if you happen to have a way to coincidentally maybe compute the mass of the universe, that factor may be used to determine the limit of charge in universe. Okay. Keep that in mind, as well as units of action. All right. So why am I talking about this? Because we do this here. So we'll do the Planck force. All right. So the Planck. I'm going to abbreviate it because I know I'm going to run out of room. Actually, we'll just do it lower. We'll do it lower so we have plenty of room. All right. Let's go down. So do the Planck force. Set that equal to the mass of the universe. Mass universe. Put in apostrophes little u. Well, that's going to be times c squared. So the mass energy of the universe. And then we're going to divide it by the radius of universe. Okay. I know, we're using high school math here. Exactly. Why do you have to make things more fancy? Now, if you're required to be more fancy, by all means do that. Okay. So what we got? So the claim is that the Planck force, if you set that as basically a constant, and you were to have mass of universe, the mass energy, you would be able to determine the radius of universe, or vice versa. Let's give it a try. So, here we go. All right, so let's share over here. All right, so let's do this. We just go right over here. Okay, so I'll just clear that out, and we'll just literally just type in natural language, Planck force. We'll set that equal to, let's just do this. X kilograms times c squared. So we're going to solve for x. That's literally what we're doing right there. Okay. We're going to solve for the estimated mass of universe. I put an equation in from the last video in Livestream. So let's see if perhaps we can verify. Okay. So the radius of universe we've claimed is going to be meters squared divided by the Planck length, because we happen to be a fan of maximal extendability. What is maximal extendability? AKA, there's no arbitrary boundaries, and I would claim nothing but ratios from Julian Barbour. All right, let's put that on there. Let's solve for x. Okay, so it's got all this stuff. So it's expressing the Planck force over there. It's giving us a conversion factor. Oh God, that's a giant number. Remember, we're solving for kilograms, so let's throw kilograms in there, so we can kind of get an estimate of the magnitude. Okay, so it's that many kilograms. Hold on, let me swap over to grams. Okay, 10 to the 64 grams, and that's 1,000 grams per that, so it's approximately 8 times 10 to the 61 kilograms. That was coincidentally what we had gotten before. So let's just take this. Hold on. The next two numbers are 1 and 5. And then our error comes in. So we're just going to take this here. Let's go back to our other equation and take a look at it the other way. And since algebra is awesome, we'll just go right here. And let's just plug in that number. Kilograms, and then we'll just solve for x meters. Well, for x, meters, because we're using coherent units, so we can. God, that's also a really big number. Not quite as many digits, but very large. Oh, that's good. All right. So as we can see here, okay. 6 times 10 to the 34. All right. Oh, we got to add meters. Forgot. I apologize. Okay. So that's going to be, all right, kilometers, and then we go to meters. All right. So 6 times 10 to the 34 meters. Wait a second. If we use that there, that looks a lot like meters squared over the Planck length. 6.187 times 10 to the 34 meters. 6.187 times 10 to the 34 meters. Huh. Might we use this as a potential clue to what might be going on?